So, good morning to one and all. Now, for this beam, we can find out the degree of static and kinematic redundancy. In the previous lecture, we have discussed the degree of redundancy for the beam and the frame. And today we have taken the two more examples, which is related with the beam, frame, and the truss. So, here the continuous beam is there. The support A is fixed. The support A is fixed. Support B is related with the roller support, and support C, that is the end C, rest on the roller support. So we can say that at support A there is a horizontal reaction, there is a vertical reaction, and the moment. These are the three unknowns, or R is equal to 3. Reaction components are 3 for the support end, support A. Support B, there is a reaction which is vertically upward direction, that is the perpendicular to the plane, as a roller is there. And support C also, again there is a vertical reaction. So we can say that R is equal to, so R is equal to 3 plus 1 plus 1, that is the 3 plus 2, that is 5. Okay, so DSi, degree of static redundancy, DSi, that is equal to, we can say that R minus E, that is the external redundancy, and the internal redundancy, or in case of beam it is always 0. Okay, so R is equal to, in this problem, 3 plus 1 plus 1, that is 5, and the number of equations available are 3. Therefore, we get the DSi is equal to 2. Degree of static redundancy is equal to 2. Okay, but what about the kinematic redundancy? At the support A is fixed, that's why the horizontal translation, vertical translation, and the rotation, all three are 0. That's why at support A, there is no translation, no rotation. But at support B, this support can be moved in X direction. That's why UB is there, right? In vertical direction, reaction component is there. That's why it's restrict the movement in the vertical direction. That's why V is 0. VB is 0. But due to application of load, beam bend like this. This is the elastic curve, and therefore when we here the theta is 0 at A is 0, but B it is there. So theta B is there, theta B towards A, because the roller support is there, and here theta B towards C. So theta BA and BC at support B, it will move like this, and at support C, theta C is there, and due to roller support we can say that the U at C is there. So 2 at support C and okay, 2 at support C, and we can say that the at B there is a movement translation along X direction, that is UB, and the uh, theta B to A and B to C. So 2 plus sorry, so theta B to A and B to C is same, therefore theta B is there, only one theta angle is there, and the UB is there. So 2 plus 1, 3. So the DSi, DKI is equal to 3, right? Okay. But in case of the frame, in this frame, these are the closed area. This is the 1 and this is the 2. Therefore, the value of A, that is the closed area, is equal to 2. So, DSi is equal to, the formula is same, but external is equal to R minus E, and internal is equal to, we can say that, the 3 times of A. And therefore, for this given frame, we can say that the value of R, is equal to, here 3 unknowns because the support is fixed. Here is also 3, 3 and 3. So 3 multiplied by 4, 12. So here reaction components are 12. There is no internal hinge. All the supports are rigid, and that's why 3 equations are available. So 12 minus 3, it is, we can say that, 9. Externally 9, and internally we can say that the 3 multiplied by closed areas are 2. So 3 multiplied by 2, it is 6. So plus 6. Therefore, its value is 15. So DSi external plus internal is equal to 15. So this is the static redundancy. But kinematic redundancy, again we have considered, this is the support A, B, C, D, all are fixed. That's why the at each support DKI is 0, right? But at every joint there is a slope. So theta 1, this is second theta, this is third one, right? So at this joint, fourth one, fifth one, and sixth one, and at the last end, 7. These are the 7 thetas. Similarly, at this point, the joint will be moved like this. That is the translation, which is same at the force level, that is delta. So delta for 1 to 2, or we can say 2 to 3, it is same. Delta, here also delta, and here also delta. So 1. So total theta is 7, plus 1 translation at this level, second translation at this level. That means it will be move like this, and this value is say theta. So theta at lowercase 1, this is say theta 1, and this is say, sorry, delta 1, and this is delta 2. This is also delta 2, and we can say that the delta 2. So 1, 7 plus 1, 8, plus 1, 9, and plus again at this joint, again there is a translation. It may be shifted somewhere here, okay, and that's why we can say that plus 1. So 7 plus 1 plus 1 plus 1, that's why the DKI is equal to 10. Okay, so for the frame, we have considered kinematic redundancy is related with the rotation, that is the theta. As the joints are rigid, therefore we can say that at every joint only one theta is there. But if there is an internal hinge, definitely number of joints are number of members are connected. That will be think. For example, if the at particular joint, if the internal hinge is connected with the 2 member, then we can add equation, one more equation. 3 members are connected, then 2 more equation. 4 members are connected, then 3 equations. We can add in the R minus E equation. Okay. So let us move toward the second one. Second is again, we can say that the truss. For the definitely truss, we know that as per the assumptions, whatever the, we can say that the external redundancy and internal redundancy. For external redundancy, again we have used the same equation, R minus E. But for the internal redundancy, we have considered the on the basis of the number of joints and number of members available. So for this truss member, we have considered the equation DSi is equal to DSi external and DSi internal. So DSi external is equal to, so DSi is equal to again R minus E. That is the, we can say that the DSi external. Okay. So this is the post equation, plus we can use M is the number of member minus 2 times of joints minus 2j minus 3. This is the equation which is used for internal redundancy. So let us consider here this truss is a rectangular shape, and that's why we can say that generally truss consists of the triangular members. That means the at least um, if triangle is there, then we can say that the truss is stable. Otherwise, if rectangle is there, pentagon is there, we can say that the truss is not stable, it is unstable. Okay, so let us start. DSi external, here the hinge is there, that's why two unknown, horizontal and vertical reaction, and roller is there at another support 1. So 3 minus, equations available are 3, therefore it is 0. But about the internal, M number of members are 4 minus number of joints are also 4. 2 multiplied by 4 minus 3. So 4 multiplied by 2, 8 minus 3. That's why we get the 5. So 4 minus 5, it is minus 1. So minus sign indicate the truss, or we can say that the frame is unstable. And if we have applied at least one member, then it will be stable. So this is the degree of redundancy, it is minus 1. And regarding the kinematic redundancy, for kinematic redundancy, we know that all the joints are pin connected. That's why moment is not applicable. Rotation is not allowed. So we can say that for every joint, we have considered the dki is equal to 2. So here it is observed that there are 4 joints, 1, 2, 3, and 4. So 4 multiplied by 2, that is 8. But here it is observed that at joint A, there is a hinge, and that's why it restricts the movement in x direction and y direction. That's why it is 0. So we can say that for two joints, it is 2 multiplied by 2 plus here 0, and at this roller support, vertical movement is restricted, but horizontal is possible because of the roller. So it is 1. So 2 multiplied by 2, 4 plus 1, that is 5. So degree of kinematic redundancy is 5 for this. Similarly, here I have considered 2 multiplied by 4, that is 4 joint, but here because of the hinge, we can reduce the 2 equation because it restricts the movement along x and y direction, both directions. So 2 and 1 along the vertical, so 3 minus 3. So 4 multiplied by 3 minus 5, that is 8 minus 3, that is 5. So we get the degree of kinematic redundancy is 5. Similarly, for this truss, here it is clearly observed that externally redundant because at support A, hinge is there, support B, roller is there, and one more roller is observed at C. Therefore, it is 4. So R is equal to 4 and R is equal to 4, right? And the equations available are 3. So 4 minus 3, it is 1. ठीक है. But regarding the internal redundancy, again we can say that it is 0. Why 0? Because all members form the triangle at every joint. So number of members are 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. There are 9 members, minus number of joints are 1, 2, 3, 4, 5, 6. 2 multiplied by 6, it is 12, minus 3. So 12 minus 3, it is 9. 9 minus 3, it is 0. And therefore, it is internally determinate but externally redundant with degree 1. Right? Regarding the kinematic redundancy, here at 3 joints, 1, 2, 3, to translation, rotation is not allowed. So 2 multiplied by 3 plus at joint A 0 because the translation along X and Y is restricted. But translation at B along X direction is possible. Similarly at C, same. That's why 2. So 3 multiplied by 2 plus 2. So it is 8. So the degree of kinematic redundancy is 8. So this is related with the, we can say that, static and kinematic redundancy for the beam, frame and the column. So this is the last problem related to the degree of redundancy. So let us discuss this problem. In this problem, we can say that there is a frame, and this frame is connected with the hinge at support A and roller at support B, and the load is applied. But from redundancy point of view, we are not related, we are not consider the which type of load is there, but we have considered only the reaction component and the equations available. So here it is observed that at support B, roller is there. That's why we can say that support B, there is a horizontal reaction. Support A, hinge is there. That's why there are two reaction component. Let us say these are the assumed direction. So this is 1, this is 2, and this is 3. So again, we have considered, again it is open. So DSi, degree of static redundancy, is equal to R minus E. R is equal to 3. Number of equation available are 3. And plus it is open. That's why it is 0. So the answer is 0. It is determinate and stable. Regarding the kinematic redundancy, that is the DKI. Again, here it is observed that at support A, horizontal and vertical translation are restricted, but it can be deflected. That means the rotation is allowed. That's why theta A is there. Okay. At B, we can see that the roller support is there. That's why it can move easily in vertical direction. So VB is allowed and rotation is also allowed. That is the theta B. So this is the 1, 2 and 3. So dki is equal to 3. Now in this beam, the DSi, degree of static redundancy, is equal to number of equations are 3, number of reaction components are 6. That is the 3 at every end because both ends are fixed. Therefore, it is 6 minus 3. And similarly, additional equations available due to the hinge, because we know that at hinge moment equation is always 0. That's why we have developed the two additional equation because two hinge are there, 1 plus 1 2. So it is 6 minus 5. The answer is 1. So degree of static redundancy is 1. Okay. Similarly, when we have considered degree of kinematic redundancy, at this point definitely the theta is 0, but here theta is there, and theta here is also there. Okay, so dki, for dki, we can say that definitely at every support dki is 0, but at hinge support we can say that it can move in upward direction or downward direction, that is the vertical direction. So V is allowed here. Second, theta is also possible, that is theta from, say, this is the B and this is, say, A. So B to A, theta B to A, and theta B to C. That means this is the, say, support C, this is support D. Okay. Similarly, at every support, at hinge C, again there is a vertical translation. So V is again allowed, VC is allowed, here VB is allowed, theta BA, theta BC. So we can say that the 4 number of degree of kinematic redundancy is equal to 4. So thank you very much. So I think using this simple concept, degree of static redundancy is equal to external redundancy and internal redundancy. External redundancy is related with the reaction component, that is the external support and the equations available, and internal is depend on the type of structure. For in case of beam, it is 0. In case of frame, we have considered 3 types of A. A is the closed areas. And in case of truss, we have considered M minus 2J minus 3 in bracket. And for the cantilever truss, generally cantilever truss, we can analyze from the free end. And that's why even though both ends are hinge, external hinge, even though we can analyze, and that's why it is cantilever truss is always determinate externally and internally depending on the number of members. And that's why the equation, instead of M minus 2J minus 3, we have considered M minus 2J. So